Hi, I'm Jed Doherty, VP of Field Engineering at Dataiku, and I'm here today with Ian Stoica. We're going to be talking about reinforcement learning. Ian's a great person to learn about reinforcement learning from, since him and RISELab are responsible for creating some of the most widely used tools in the data science community, including Spark, Mesos, and most recently Ray. Ray is particularly applicable to our current topic, as it was initially developed with reinforcement learning in mind. In addition to leading RISELab, Ian co-founded Databricks and was its first CEO. So let's jump right into the questions. How is reinforcement learning a paradigm shift from the classic supervised learning process that many of us are pretty familiar with? This process being kind of we collect tons of data, run a big train, deploy a model, then wait for it to start degrading in performance to update it. What does reinforcement learning make different from that?
Yeah, thanks for having me. Very happy to be here. So, like you mentioned, the supervised learning, which is used in many successful applications today, image recognition, language translation, and many more, it fundamentally tries to associate an input with an output. It tries to learn a mapping between inputs and outputs. In contrast, reinforcement learning is about interacting with a world, with an environment, and trying to maximize some reward. So in reinforcement learning, you have an agent which observes the state of the environment, of the world, and make decision. We may change the state of the environment. And the goal of this agent is to maximize this particular reward. And in the process, it's going to learn a policy which will guide its actions based on the current state of the world. Is going to make a particular decision. This is what policy is going to provide that next decision. And there are many examples. Probably, as you know, some of the most famous ones are playing games, including Google's AlphaGo, and many DeepMind's reinforcement learning systems and algorithms to play Atari games. And in those cases, it's very clear, right? It's like, for instance, if you play a Go, an action is to move a piece on the table. In the environment is a layout of the table with all the pieces, black and white. And the reward is winning the game. And one particular thing about where the name is coming from is that, you do not, in reinforcement learning, you do not have labels like in the supervised learning. You just take the actions and then you see what is the outcome. So you play the game, you move the pieces, and at the end, if you win the game, then you are going to reinforce the moves you made in that game. If you are going to lose a game, you are going to negatively reinforce the moves of that game. So next time it will be less likely to make the moves who led to a lost game previously, and it's most likely they are going to make the moves which led to a victory previously.
So with reinforcement learning, a big part, it sounds like, is you don't necessarily have to do this data collection and data preparation process. Is that the case? Like, what is it, if you're starting on a reinforcement learning problem, what kind of things do you start putting together?
Yeah, so it depends. It's a good question. It depends very much about the problems you are trying to solve. So for instance, it's true that in the case of playing a game, collecting the data happens during the playing itself. So you don't need to a priori collect the data. So of course, if you have, it's again, the goal of the reinforcement learning of the agent is to build this policy, which will lead to maximizing the reward. And this policy fundamentally takes, observe the environment, and based on that observation is going to make a decision, which hopefully will lead to maximizing the reward. So now you can use, if you have data, to train this policy a priori, and then to refine it while you are playing, say, the game or resolving the problem, but it's not necessary. And this was what, in some sense, was point was illustrated by AlphaGo, which initially they used all the database of the existing games to learn reasonably policy and then refine it also during the games to AlphaZero. With AlphaZero, used no prior information, and eventually AlphaZero was a better program than AlphaGo.
With just pure iterative learning instead of preceding
just
it
pure
with that
iterative
data.
learning. And it's not like you do not need data in the reinforcement learning. By the way, to acquire the data you need is by interacting with the environment and observing the reward.
Cool. So like generative creation of data.
It's like what humans do, like we do. We interact with the environment. We have a particular goal, and we take the actions so to achieve that goal, right? Going to the airport, any of these many examples you do every day. Well, not every day now. You are not going to the airport anymore. So, but preparing your breakfast and other things.
So some of the examples, or a lot of the examples you've used for reinforcement learning so far, are games where you have complete information. I guess you know the whole chessboard, or you know the whole Go board at once. Can reinforcement learning also be applicable in games with incomplete information?
Absolutely, and in the most practical cases, you do have incomplete information. Like, for instance, if you are going to use reinforcement learning to guide a robot how to get from A to B, the robot will only have observation about the environment through its sensors. Images, radar, maybe sound, and he's going to navigate. He's going to navigate only based on this information, because this information is the only thing the robot has to capture the state of the environment. The same obviously thing it's in self-driving cars when using reinforcement learning.
Right. We don't have a map of the entire world built into them from overhead or anything
Absolutely.
like that. They're learning as they move. Okay.
Yeah.
So when we think about some of this terminology used in reinforcement learning, agents and simulation, it evokes a lot of mathematical and kind of psychology ideas, tests on rats in a maze, that sort of stuff. Is this a coincidence? And what is this history of reinforcement learning that it leverages all these ideas?
Yeah, that's a good question. So actually, there are multiple threads which came together to create what is today reinforcement learning. And these threads came together only around 1980s, actually. Still a long time, but compared to when these threads have started, it's not that long ago. So there are a few threads. So one thread is about learning by trial and error, and this is psychology and studying the animal behavior. And for instance, the Edward Lee Thorndike had this great experiments with a cat. You put in a puzzle box and observes how the cat actually learned by trial and error to open the box by using some latches, moving some latches. And once the cat opens the box, then the cat is going to get a reward, like a good meal. And he demonstrated for the first time how animals are very successful by using this trial and error to learn a new behavior. And then once you learn it, and the next time the cat in the box is going to open the box faster and faster and faster. So that's one thread. The other thread is coming from operational research, and engineering in general, it's optimal control. So this is about optimizing some processes or chemical processes, or there are this. One particular example you've ever played is that when you land a spacecraft, or say on the moon, right? You need to control the thrust as a function of the mass of the spacecraft, the velocity, and the height, so that you can, land without crashing. So that process, how you're, of controlling the thrust to land smoothly is what optimal control is about. There are also other from programming language, from computer science. It's a dynamic programming. It's obviously a way to compute a solution which subdivides a problem in smaller problems, and actually they observe that, take advantage of that many of these sub-problems are actually part of the same instance. And then it computes only once the solution for that instance, and then it's reusing it over and over again to reduce the complexity. So, and then it's also Markov decision process and things like that. So there are many things which are coming together, and kind of they coalesced in around the 1980s to create what we know today as reinforcement learning.
So reinforcement learning, in my mind, well, and maybe in the public's mind, if you ask some Joe on the street to describe AI, he might describe something much closer to reinforcement learning than to supervised learning, right? As something that iteratively learns about its environment and the best way to perform actions over time. Sounds a lot closer to AI than, okay, we dump a bunch of data in here and find some patterns. Why do you think that supervised learning has kind of, up until recently, been the predominant use case in industry, more so than reinforcement learning?
Well, for two reasons. First of all, it's with supervised learning, you still can solve a lot of very practical problems about cognitive recognition problems, right? Problems like humans are doing it subconsciously, right? And the second thing, it's easier, especially when you have data, right? You just need to learn a mapping between the inputs and the outputs. With reinforcement learning, you actually need to almost learn like a program, right? Because reinforcement learning is about a sequence of decisions to get to a result, the desired results, to maximize the desired reward. So I think, these are one of the reasons. And it's again, like you mentioned, you need, with reinforcement learning, you need also to interact with the environment to learn, these policies. And that interaction can be slow. It's like it can take a lot of iteration, a lot of interaction with the environment to learn a good policy. The reason we saw a lot of successes in the gaming is because with gaming, it's easy to simulate them, right? And it's easy, right? So you can do these trials. I have a policy, I'm going to test it, and I see how it's performing, and I'm going to improve it. You can do it very fast. But if you think about a robot which is working, which is navigating in the real world, the interactions are much slower. It can lead, to some physical damage of the robot if you make the wrong decisions. So it's more expensive, slower, and that's why it takes much longer. So that's why it's more difficult.
Right. I can run a game over and over, but I can't run the world over and over. Or I can maybe distribute a game in parallel, but I can't put the world in parallel.
Yeah. So that's why you see that a lot of work in reinforcement learning, even for solving practical problems, rely heavily on simulators, right? You have driving simulators. You can have simulator for a manufacturing process, and many more.
Is it fair to say that your reinforcement learning algorithm is going to be only as good as the simulations you're training it on?
Not really, because once you learn in a simulator, hopefully, and there are many solutions out there, but hopefully you have a good enough good enough policy. So when you are going to deploy it in the real world, you are going to continuously refine it. The nice thing about reinforcement learning is continuously refining it, continuously interacting with the environment, and then it's going to improve its policy, right? So in some sense, simulation can provide you a good starting point, which will allow you to be much more efficient. You're going to enable the agent to be much more efficient in tuning and refining the policy in the real world.
So we can start it with a simulation and then let it finish in the real world.
Yeah, it has a name, a sim to real, and there is a lot of work on that.
Amazing. So I wanted to talk a little bit here towards the end of the session about Ray. So Ray is one of the fastest growing open source projects in the world right now. And it's sprung out of your lab and in some ways out of your mind. Can you tell us a bit more about it and its roots in reinforcement learning?
Yeah, so we started Ray because what we wanted to do is to scale up some machine learning algorithms. And soon when we started Ray, initially with distributed training, we started to focus on reinforcement learning. Because reinforcement learning, it's not only very promising, but like we discussed earlier, it's very demanding. It's a very difficult workload. If you think about reinforcement learning, it's like you need to do inference, you need to do training, you need to do large-scale simulations, and you may need also to do some data ingestion and processing. You need to do inference because this is what the policy is doing, the agent is doing. It's looking at the environment, think about the observation of the environment. It's like a query and makes a decision. The decision is like an answer to the input, which is a state of the environment. Then, as you are going to interact with the environment, you are going to get new data points, and then you are going to use these data points to train and to improve the policy used by the agent. So this is training. Then the way you are going, like we discussed, in many cases, the way you are going to evaluate these policies is you are going to do it by performing simulations, and you are going to do lots of simulations at the same time. And when you are going to interact with the real world, you are going to get the observations through sensors, so you need to process this data to make sense of the world around you. So fundamentally, it's all this workload. So you need very generic framework to support these workloads. And as a proof point that this is indeed, it requires a pretty bespoke system. If you look about some of the leaders on the reinforcement learning, like OpenAI, DeepMind, and so forth, they build their own systems internal, even for new algorithms, which they build a system for a new algorithm, they build new systems. And that's obviously, it's very time consuming and so forth. And our goal was to build a system which is general enough that is going to support reinforcement learning, and this is what we built Ray. And because reinforcement learning is such a general workload, Ray is also going to be useful for many, many other workloads. And the key reason of why Ray is general, to put in a nutshell, it's basically takes the two concepts you have in almost any imperative language, and that's functions and classes, and allows the programmers to execute this function remotely and instantiate the classes remotely and asynchronously. And this asynchronicity is providing you ability to run multiple tasks and instantiate multiple classes. We call the instance of a class an actor in parallel. So that's how you get parallelism and scalability. So it's a very flexible and general language and framework.
Fantastic. Well, thank you for building it and releasing it into the world. We've reached the end of our time here. We'll be moving over towards the questions. Thank you so much, Ian. It was illuminating, and I really enjoyed the conversation.
Thank you so much.